In this video, we will introduce the renewed software-defined massive MIMO system and the inner working on this hardware that allows coherent beamforming operation. The base station, commercially trademarked as Pharos, is a product of Skylark Wireless LLC, a spin-off of Rice University based in Houston, Texas. As shown in the right-hand side picture, Pharos is composed of multiple radio heads stacked on top of each other, as well as a central unit called the hub. Each radio head has a 1.5U form factor and includes either 8 or 16 independent digital radio transceivers. This number depends on the band of operation to preserve the half wavelength antenna spacing. Each transceiver is connected either internally or externally to antennas. This picture in the left-hand side shows inside of a radio head were 4 dual polarized BRS band antenna elements attached to 4 dual channel software-defined radios called Iris. The hub connects to radio heads through fiber cables, with each fiber carrying data with a maximum rate of 12.8 gigabit per second. It also provides 48-volt DC to them through individual power cables. It can support up to 6 power and data ports to radio heads. It is also possible to daisy chain 2 radio heads together, thus supporting up to 12 radio heads in a Pharos base station. With maximum 8 antennas in radio heads, the Pharos base station can support up to 96 antennas. The hub provides 4 10 gigabit per second Ethernet fronthaul links to connect to an external compute node, such as a CPU server. Note that while the hub's fronthaul is Ethernet compatible, the radio heads are not, so they cannot be directly connected to commercial off-the-shelf switches. The main building block for the Pharos is the Iris software-defined radio. Iris is using a Lime microsystem LMS7002M dual-channel software-defined radio transceiver with tunable center frequency from 50 MHz to 3.8 GHz. While the LMS7002M chip supports an instantaneous bandwidth of 60 MHz, current Iris firmware supports only up to 40 MHz. LMS7002M supports a nominal continuous wave power output of 0 dBm. Iris can be equipped with a modular front end in a plug-and-play fashion. There are currently 3 types of front ends for Iris covering different target bands. The depth front end shown in the right-hand side simply breaks out the 2 RF inputs/outputs of the LMS7002M to SMA antenna ports. It can be configured for both TDD and FDD operation through an onboard RF switch. No amplification is done on the signal in the front end. Thus, its primary use is for indoors benchtop experiments. The BRS/CBRS front end is a dual band module which is designed for filtering and amplification in the BRS band from 2.5 to 2.7 GHz and CBRS band from 3.55 to 3.7 GHz. It amplifies the continuous wave power of the LMS7002M chip by 28 dBm, and it only supports TDD operation. The UHF front end is all similar to the BRS/CBRS front end, except it supports the UHF band from 400 to 700 MHz. Iris onboarding processing element is the Xilinx Zinc 030 system on chip, which includes FPGA fabric and a dual-core ARM processor on the same chip. Iris is an Ethernet-based device. is equipped with an RJ45 Ethernet port that is used in a standalone operation, for example, as a client to Pharos. Through this port, Iris supports Power over Ethernet or PoE functionality and can be powered up when connected to a PoE-enabled network switch. One of the unique capabilities of the Iris is the daisy chaining capability, as shown in the bottom right picture. This capability is made physically possible through male and female side connectors, which allows the irises to share power, data, and a common data bus. At the functional level, this common data bus is enabled through the GTX transceivers on the FPGA fabric and Xilinx's Aurora IP logic, which achieves a maximum 12.8 gigabit per second streaming data rate. The daisy chaining automatically locks all irises in phase through the clocking structure that is implemented on the iris. We will look more closely at this structure in the next slide. A phase locked, or in other words, frequency synchronized iris chain can therefore perform coherent MIMO operations. Usually, a chain of 4 or 8 irises are packaged as a radio head to become part of a Pharos space station, as was shown in previous slide. As mentioned earlier, an iris daisy chain is fully phase locked through a clocking structure implemented on each iris. At the heart of this structure is a jitter cleaning clock buffer, where it receives an input clock either from a local oscillator with a 52 megahertz output, or from an upstream iris, or if the iris is first in the daisy chain, by recovering the clock from the Aurora link to the Pharos hub. As mentioned earlier, the Pharos hub is responsible with distributing a reference clock to all the radio heads. The master clock source on the hub that feeds all the radio heads is programmable. By default, it uses a highly accurate Scilabs 5356 local oscillator with frequency stability of 100 parts per billion. The clock source can also be programmed to use an external clock, for example, from a GPS source. Lastly, it can be programmed as a Syncy slave, where it recovers the clock from the first 10 gigabit Ethernet frontal port and uses that as the reference. For any beamforming operation, a tight time synchronization between all radios is required in any massive MIMO base station. In Pharos, this process is somewhat more complex than systems that don't have a daisy chaining topology. In a daisy chaining topology, sending a sync message from a central node is not received at the same time at all nodes, since it has to flow through the daisy chain. However, given that the message goes to FPGAs, the hop delay is fixed and can be measured during the initialization. In Pharos, through a software command, the hop broadcasts a sync message to all radio heads through the data line. Each iris on each chain routes the message downstream until it reaches the last iris. At each iris, a counter is initialized as soon as a sync message is received. The last iris, loops back the message upstream, and upon receiving the loop back message, each iris stops its counter and latches the value divided by 2 as delta. Later on, when a trigger message is sent by the Pharos hub to perform a synchronized task, each iris applies a delay delta to the trigger message before starting the task. This guarantees a tightly synchronized task by all irises.